Welcome back to our discussion on states of matter. It is the third class in this unit, where we have thus far discussed about intermolecular forces. We looked at ion-ion interaction, next was ion-dipole interaction, third is dipole-dipole, fourth is hydrogen bond. So, we did these two things in the first class and these two things in the second class, and today we will wind up by looking at dipole induced dipole and induced dipole induced dipole. That will round up our discussion of intermolecular forces. We then would move on to the properties of gases and liquids. So, this is what we will look at today. So, the take home message from all this is the functional form. So, we need to remember the functional form of the various intermolecular forces. We also need to know the order of the strength of intermolecular forces. And dependence on various properties. So, as an example of what we discussed in the last class, let us try and answer the following question: which of the following molecules have a dipole-dipole interaction or show dipole-dipole interaction? And the choices are carbon dioxide, second is dichloromethane, and third is methane itself. So, to do this, what do we need to know? We need to know the structure of the molecule. The first thing that we need to know is to know the structure of the molecule. So, that is what we need to know. Presumably, we know the structure of carbon dioxide, these three molecules. Carbon dioxide is like that, dichloromethane is like that, it is a tetrahedral molecule, and methane again looks similar, but with all four identical. The second thing that we know is qualitative idea about the electronegativity of various elements. You do not need to know the quantitative values, but the periodic trend of the electronegativity is something that you would need to know. So, we know that oxygen, for example, is more electronegative than carbon. Similarly, chlorine is more electronegative than carbon. The carbon and hydrogen electronegativities are not that different. So, typically we will imagine that this is non-polar. So, why do we need to know the electronegativities? We need to know the electronegativities to determine if a bond is polar or non-polar, or so as a result if it is polar, then you will get a dipole that is created. So, one needs to know this to know whether it has a dipole-dipole interaction. And once we know this, we do vectorial addition to get the total dipole. So, in this particular case, this is polar, carbon dioxide is polar because oxygen is more electronegative than carbon. So, you will have one dipole like this, but you also have a symmetric dipole in the opposite sense. As a result of this, this has no net dipole moment. So, at equilibrium there is no dipole moment, although each of the carbon oxygen bonds is polar, because of the symmetry in the molecule there is no net dipole moment. In the case of dichloromethane, you have one dipole oriented along one carbon chlorine bond, another dipole moment oriented along the other carbon chlorine bond. We said that because the electronegativity difference between carbon and hydrogen is not very high, we are going to say that these two bonds are non-polar. So, effective dipole moment is determined by these two vectors, one vector here and another vector here, and we do vectorial addition. So, we are going to find that there is a net dipole moment in this direction for dichloromethane. If I use the same logic for methane, then you will find that in this particular case again there is no net dipole moment. So, then in the following molecules, carbon dioxide, dichloromethane and methane, the only molecule which has a dipole-dipole interaction is dichloromethane. Now, let us look at another molecule and try and predict another physical property. So, this illustrates something else that we learnt yesterday. So, predict the relative boiling point of acetic acid and methanol. This question involves the concept of hydrogen bond that we learned yesterday. So, we take these two examples. So, acetic acid, the structure looks like this. So, to have a hydrogen bond, what are we saying? We say that if you have hydrogen attached to an electronegative atom, then hydrogen attached to an electronegative atom. Then it's a prospective hydrogen bond situation. So, if you had this, you write another molecule of acetic acid, but in the opposite orientation, and now you can see what would happen. You have the possibility of a hydrogen bond here, and you also have a possibility of a hydrogen bond here. So, each molecule of acetic acid could in principle have two hydrogen bonds. Now, you compare this with methanol, and this is also satisfies the case situation where you have an hydrogen atom attached to an another electronegative atom. So, in principle you could also have in this situation a hydrogen bond with another molecule of methanol. So, this also could in principle undergo hydrogen bonding, but the difference is that in acetic acid you have the possibility of 2 hydrogen bonds as opposed to methanol, where there is only 1 hydrogen bond, and this one the strength of the hydrogen bond is also higher than in the case of this, because this is an acidic proton. So, if you put all this together, you expect that the boiling point of acetic acid, we expect to be higher than methanol. The other thing that you have to observe in these cases is that if you have more than one, that is, if you have 2 interactions, one generally finds that it is not additive. So, you will find that the property as a result is going to be significantly higher than just 2 times if you had a single interaction. Okay. So, these are 2 examples of things that we learned yesterday. One was the dipole-dipole moment, the other was hydrogen bond. So, now we will move on to the next thing, the next intermolecular interaction that we need to look at, and that is the case of dipole-induced dipole. If you look at water, water supports life, that is of fishes and etc., which means that it has oxygen dissolved in water. Now, oxygen, or for that matter nitrogen, but oxygen is a non-polar molecule. There is no dipole, and it does not support a hydrogen bond because there is no interaction. So, it is not ionic, it does not have a dipole, it does not have a hydrogen attached to it. So, you will start to wonder what happens, what is the reason for the solubility of oxygen in water. So, we will try and understand this. We know that we have a dipole in water. So, we have this and we have this, we have now become good at this. We add these 2 things and we find a dipole vector in this direction, a net dipole. And if you bring an oxygen near this, this dipole will generate another dipole close to this. So, what it means is that the presence of a dipole, this is a permanent dipole. The dipole in water is a permanent dipole, and it generates a dipole in the oxygen, and this is an induced dipole. In other words, as a result of this dipole of the water coming close to oxygen, you expect that there would be an interaction and the electron density would be polarized in oxygen in such a way that you will have less electron density here and more electron density there. So, you will get a delta plus delta minus situation, but this is in the presence of a dipole which, so this permanent dipole leads to an induced dipole here. So, the next question that we will ask ourselves if you do this is, if I took oxygen and if I took nitrogen, does the extent of the dipole created, are they the same or are they different? So, the dipole that is created in oxygen as opposed to nitrogen, we wonder whether this is smaller or bigger, right. So, that is the question we would like to know. What determines the size of the induced dipole is a property which is called the polarizability. So, the polarizability is given the symbol alpha. Now, alpha measures the size of the induced dipole. And you can understand this in a simple fashion. Imagine that you have a dipole. This will generate an electric field at various points in space. So, if I have a dipole like this, I have lines of force like this, and if I have a molecule such as oxygen at some point, there is an electric field that is created by this dipole at the location of the oxygen, and this induces a dipole moment mu induced, which is proportional to the electric field at the location of the oxygen through this parameter alpha. So, larger the alpha, larger is the induced dipole. Let us try and get a sense of the kind of sizes that the value of alpha has for some compounds. So, here I have listed the polarizability whose units in CGS is centimeter cube. So, it has the unit of volume, and I have the molar mass and the boiling point. So, the molar mass I write in AMU and the boiling point in Kelvin, which in a later section you will know that convert from degree centigrade or Celsius to Kelvin, you have to add 273.15. So, the first molecule that we look at is hydrogen. It has a polarizability of 7.9, its molar mass is 2 AMU and has a boiling point of 20 Kelvin. Oxygen has a polarizability of 16, a molar mass of 32 and a boiling point around 90 Kelvin. Nitrogen has a polarizability of 17.6, molar mass of 28 and a boiling point of 77 Kelvin. Now is where things get a little bit more interesting, pay a little bit more close attention to this. I take methane, its polarizability is 26, its molar mass is 16 AMU and has a boiling point of 109 or so Kelvin. Now, we go on and to the next page I continue on this, and this is where you will have to see the trend in going from methane to the next hydrocarbons. So, that is what we will do in the next slide. C2H6, the same things, polarizability in centimeter cube 44.7, molar mass 30 and boiling point 185. Propane, which is the next higher homologous hydrocarbon, has a polarizability of 62.9, molar mass about 44 and 231 is its boiling point. And you go even bigger, CCl4, polarizability of 105, molar mass about 154 and is 350. And chlorine, just for comparison, polarizability of 46, molar mass of about 71 and 238. So, what do we learn from this? So, if you looked at this again, when you go from CH4 to C2H6 to C3H8, alpha increases, that is polarizability increases, and we also find that boiling point increases. This implies that if you go to higher and higher, larger the molecule, you are going to find that these kinds of interactions that involve an induced dipole will increase. So, you can almost predict what will happen if you went from C3H8 to C4H10, you could predict that the next thing that you are going to find is its boiling point is going to be higher than 231 Kelvin. Now, naturally you could ask, if I had C4H10, so if I took C4H10, you could have more than one variety. So, you could have normal butane, this which is normal butane, or you could have this. If you had this, then you will find that this has a higher boiling point. So, you will find that the straight chain analogues, because of its length, so larger the molecule, more polarizable. And more polarizable means higher the boiling point. That is why you find that in petroleum fractions, as the size of the fraction increases in going from butane to pentane to hexane to heptane to octane, this goes from being a gas to liquid to then paraffin wax, which is a solid. So, this is a clear indication of this polarizability. This thing is also called London dispersion. These are examples of the London dispersion force, name from the person who found this, Fritz London, a German born American scientist. So, what do we find? So, the moral of the story is that as you get longer and longer chains, you are going to have larger and larger polarizabilities, as a result of which you are going to find that dipole induced dipole interactions are higher. The same is true of the next interaction. So, this was the situation where you had a dipole creating an induced dipole. But you do not need to have this. You could also have a situation where you took, for example, liquid oxygen. Now, you would start to wonder, if I have liquid oxygen, there is obviously no dipole to begin with. So, if you had this, no dipole to begin with, no permanent dipole. That is important, that there is no permanent dipole. But what that means is that if you looked at it at equilibrium, the electron density is symmetric. So, electron density symmetric at equilibrium. But you could have an instant in time where, because the electrons are undergoing motion, you could have an instant in time where you have a skewed distribution. That is, an asymmetric distribution of the electron density. So, I have tried to draw it in such a way that I have more electron density on this side and less on this side. So, I have a partial charge redistribution, and so this end becomes slightly positively charged relative to this side. So, this happens in any molecule, no matter what the molecule is, you are always going to have this instantaneous dipole creation. And what we have already said is this instantaneous, and now once I have this dipole that is there instantaneously, this could then induce a dipole on its neighbor. And we already said that the induced dipole on this neighbor is proportional to the polarizability. So, effectively what this means is that the polarizability, which then in turn depends upon the size of the molecule and its molar mass, is going to show that all properties, all intermolecular interactions will then scale with the molar mass. Larger the molar mass or longer the molecule, you are going to have larger intermolecular interactions. So, no matter what kind of molecule is this, all molecules show dispersion forces. The reason I say this is because the earlier discussions involved either ions or dipoles, but in this case no matter what the molecule is you are going to see this dispersion forces. So, now let us try and figure out if we have understood what we have discussed. So, here is some data for you. The boiling point of propane, N-butane, N-pentane and N-hexane are respectively minus 42.1 degrees Celsius, minus 0.5 degrees Celsius, 36.1 degrees Celsius and 68.7 degrees Celsius. And we would like to explain this trend. So, if you write it down, so propane is CH3, CH2, CH3. So, that is 15 and 15, 30 and molar mass of 44. N-butane is normal C4H10, that will be 48 and 58. Normal pentane C5H12, CnH2n plus 2, that is 60 and 72, and N-hexane 72 plus 14, 86 is the molar mass. And you expect that boiling point without any computation will increase as you go down, as is shown here. So, in all these cases it is the London dispersion forces that operate. So, there are two kinds: dipole, induced dipole. If you have a solution in water, for example, of a non-polar molecule in a solution which has a dipole, then you will have this situation. But all systems will show induced dipole or instantaneous dipole, induced dipole kind of interaction. And all of this I forgot to mention earlier. So, this dipole-dipole interaction, we have identified how to do it. So, the functional form, the potential energy of the London dispersion forces will vary as 1 over r to the 6, just like similar to dipole-dipole, but the proportionality constant is different. I have not worried about that. It depends obviously on the polarizability, you might have already guessed, because we said that the electric field at a particular the dipole moment that is created is proportional to the polarizability. So, the proportionality constant that relates the potential energy with this functional dependence varies for the dipole-dipole and for the London dispersion forces. So, let us now try and summarize what we have learned with a flow chart. So, if you were given a set of molecules, or if you wish to determine what is the intermolecular force that is operative in a molecule, this is how you would go about it. So, the first thing that you ask yourself is, are ions present? And there are two answers you could get to it. One is the no branch and the other is the S branch. So, if you have ions present, then you ask yourself the next question, are polar molecules present? And if the answer to this is yes, then what do you conclude? If the answer is yes, then you will say that here we have ion dipole forces. And an example would be NaCl in water. And if there are no polar molecules present, then you would say that it would be an ion-ion interaction. As for example, you would see in LICl, NaCl, Kf, etc. And we also know the strength of the interaction. I should have probably drawn it the other way around if I wanted to label it in the strength of the interaction. So, if you want this would be the strongest. So, I should have labeled it there, but I switched it around. Okay. We go through the same question here. We ask ourselves, are polar molecules present? And if polar molecules are present, we go here. If there are no polar molecules, we go there. And so, no ions present, no polar molecules present. We just discussed. The interaction that we have is London dispersion. And examples would be methane, bromine, oxygen, etc. Then once you are here and you find that the polar molecule, it is a polar molecule, then you ask yourself the question, are hydrogen atoms bonded to nitrogen, oxygen, fluorine, etc. If the answer to this question is no, then you have dipole-dipole interaction. And if the answer is yes, then you have hydrogen bonding. So, here dipole-dipole interactions, you could have CH3F, HBr, etc. And here you could have NH3, H2O, HF, and so on. So, with this flow chart, you should be able to, given any kind of question, to be able to answer some of the questions that we earlier said, to be able to identify the different finds of, to be able to list the intermolecular interactions that exist, just list them, the 5 kinds, to be able to tell the strength of each of these interactions. And if you are given a list of molecules and to arrange them in a particular order based on some physical property, on this basis and the earlier table that we have given of the size of the interactions, to be able to arrange them in the appropriate order. So, let us just discuss a few examples or exercises, and I will tell you how to, the strategy to approach each question, and then you can solve this by yourself. So, the first thing that we would like to do is to be able to identify intermolecular interactions. Identify intermolecular interactions present in ethane, methanol, and ethanol. So, what do we know? We need to know, we know its structure of the molecules, functional groups, that is polar, non-polar, etc., and the molar mass. And the strategy is determine the type of interaction in each molecule, follow the flow chart, and you should be able to arrive at the intermolecular interactions that are possible, that are present in each. So, we start, we say ethane, for example, we ask, are ions present? Yes, no. Dipoles present? Yes, no, etc. And you should be able to arrive at this, to be able to identify the intermolecular interactions that are present. This is just an illustrative example. I will give you a few more questions so that you can practice this, involving different kinds of questions. Here is another one. Rank the following in order of increasing strength of intermolecular forces in the pure substances. That is, that's N-butane, ethanol, and helium. So, again, process we follow, what do we know? And strategy. So, we need to know its structure, functional groups, polar, non-polar, etc. Without that, you won't be able to proceed. So, you need to know the structure of the molecules. In this case, fortunately, you are given the structure. You have to be able to identify the polar groups and then to use the flow chart and know the relative sizes of various intermolecular forces, interactions. Okay, that is question number 2. I will give you 3 more. So, makes that 5. Which of the following compounds? So, in the earlier thing we had to look at the strength of the intermolecular forces. Which of the following compounds is expected to form intermolecular hydrogen bonds in the liquid state? Dimethyl ether, methane, hydrogen fluoride, acetic acid, bromine, and methanol. Procedure exactly the same as before. What do we know and what is the strategy? Follow the flow chart, identify what kind of interactions are possible, and then you are just looking for where you get the hydrogen bond. So, that is a straightforward approach and you can do this. You should be able to do this at the end of these 3 classes that we have had on intermolecular forces. All right, 2 more and then we will wind up. In each pair of ionic compounds, which is more likely to have the more negative enthalpy of hydration? And to test yourself, you can say briefly explain your reasoning. First is lithium chloride or cesium chloride. Second is sodium nitrate or magnesium nitrate. And rubidium chloride or nickel chloride. So, this is a different kind of question. What we are looking at is enthalpy of hydration. And enthalpy of hydration, you should be able to rationalize what it is dependent upon. And this again has a connection with the intermolecular forces that we have already discussed. So, that is the connection. So, how does this physical property relate to the intermolecular interactions that we have already studied? And if you could do that, you can also then try and arrange it in the order of increasing enthalpies, etc., to challenge yourself. And one final question, if I have, that we will just look at is amongst, gives you a variety of questions of various types. Hydrazine, ethylene, and butane, N-butane, predict which would have the largest dipole-dipole forces and the lowest boiling point. The procedure is probably now straightforward. You should have that flow chart out in front of you. You should have a table of the strength of the table of the intermolecular interactions and their sizes, and you should just be able to analyze this and straightforwardly arrive at which molecule has the largest dipole-dipole forces and the lowest boiling point. Okay. So, I think that's given, that takes us to the end of the intermolecular forces. I think we have discussed a number of things here. So, let us just quickly summarize what we have done. So, we have done states of matter, and we said that a substance is present as solid or liquid when the intermolecular forces are reasonably are higher than the thermal energy. So, liquid or solid is present when you are going to have larger intermolecular interactions over the thermal energy. So, it is an interplay between intermolecular forces and temperature which determines whether a substance is in the condensed phase or not. And of this we said that we have ion is the biggest, then we have hydrogen bond, ion dipole. Now, it is in the order that we expect: dipole dipole, dipole induced dipole, and induced dipole induced dipole. So, this is what we have discussed thus far, and we hope that you would be able to address some of the questions that are likely to come, whether it is descriptive or applying some of the things that we have learnt here. So, now let us move on. The next thing that we need to look at is properties of gases. So, we already said when we looked at intermolecular forces that if I plotted V as a function of R, we have this, and we say that if the temperature is high, then a substance exists. If temperature is high, a substance exists as a gas. And in the kinetic molecular theory of a gas, we have already pointed out that there is a lot of empty space, and that the molecules undergo, they have random positions, and they are undergoing constant motion, random motion. And implicitly what we are saying is that intermolecular interactions in this case are small. This is a significant advantage. So, one of the fundamental reasons for studying gases is that fundamental reason is we can study systems with little or no intermolecular interaction between particles. So, the interaction is small between molecules, and the limiting case of this is no interaction. So, if we took gases, we already know that the intermolecular interaction between particles in a gas is small, and we are saying that we can take an ideal situation where there is absolutely no interaction between particles that are there in the gas, and that makes our life very simple. So, now we have got an ideal model system with no intermolecular interaction. If we can understand some of the properties there, then this is an advantage. So, this is one reason for motivation for study. Why study gases? So, one fundamental reason is that there are no interactions, and when there are no interaction between particles, it is obviously easier to study them. There is a very practical reason for this, and one is that fact that life on earth depends on the atmosphere, which is a gas. So, obviously, it is in our interest to study gases. There is also a recent practical reason in studying gases, and that is the fact that with the extent of industrialization, we all appreciate that the environment has been affected, and the environment that we live in is critically dependent upon reactions that happen in the atmosphere, which means that you have reactions between particles in the gas phase in the atmosphere. So, that is another practical reason for studying this. And historically, a number of classic experiments which proved some of the concepts that we have now come to accept regarding chemistry. For example, the atomism of John Dalton or the Avogadro's hypothesis, etc. These classic experiments were all conducted on gases. So, for this reason, we would like to study gases. So, the first thing that we will do, and it is associated with the intermolecular interaction, because we have said that in gases there is little intermolecular interaction. So, what we will do in the next classes, 1 or 2 classes, is to study gases, and we will study gases where we will first start with ideal gases where there is no intermolecular interaction. This is an ideal system, as the name implies, and then we will later look at real gases. And in real gases, we will introduce the van der Waals model for a real gas. So, that is what will occupy us in the next 1 or 2 classes. The first thing that we will do in the next class is to look at what is called Boyle's law, a classic experiment which was done and which proved the atomic hypothesis. Then we will look at the Charles and the Gay-Lussac's law, and the Avogadro's hypothesis. All very important in the way we do chemistry right now, on the way we understand chemistry right now. And then we will talk about the ideal gas equation of state. And as you can imagine, that we should be able to do at the end of this, we should be able to do simple chemical manipulations of volumes, number of moles, to given how if a gas undergoes a change from one point to another point, what is the volume change, what is the pressure change. That is the kind of things we expect that we would be able to do at the end of this exercise. We will get on to this in the next class. Thank you.